Hello. Good morning. Morning, y'all. Go ahead and pin my video. Here we go. There's your warm-up, and good morning to you. You guys there?
Yes.
Very good.
Hello, hello.
Hello.
Good morning.
No. Good morning.
Good morning.
Good morning.
Magnetic eraser.
Hi.
I'll do that while I'm doing the lesson.
That.
I'll erase something, and I'll go like this.
Some people are gonna find that kind of annoying.
Are you kidding me? I'm gonna get more. I'm gonna get more YouTube hits that way.
Yeah, true.
It's that guy that does the eraser trick.
So many subscribers.
That's called technology these days. Magnets.
Magnet,
yeah.
right?
Magnets. How do they work?
Go ahead and graph that equation, please. We'll be starting in a minute or so. Hey, rude.
Mr. Rosenthal.
Hello. $45 already. Wow. Y'all can't wait to get in here. All right, 10 o'clock. Here we go. We're graphing this. First thing you need to remember is the last thing we left off on yesterday is what's the slope? What's the y-intercept? Otherwise, you can go ahead and use a t-table. You need to be able to know how to graph using both a t-table and the equation. Straight from the equation is what I'm going to do right now. So go ahead and take another minute if you're just coming in and joining. I know we're going to get 10 or so more people coming in the next few minutes here. I know it's difficult to get up by 10 o'clock, but you know, we really work hard here at the Science Academy. And I like people are already putting that into the chat. Let me make sure I have the chat is, yeah, host only. Okay, good. Let me check the people coming in, and then I will go over this problem. Alan? With the question mark.
Mr. Rosenthal.
That's me.
Quick question. What is the slope a negative 2/3?
Yep.
Okay.
And because it's a fraction, it gives you both the delta y and the delta x explicitly. You don't have to put it over 1 to try to see what the delta y and delta x are. Delta y is the numerator, delta x is the denominator.
I'm using the x and y intercepts to graph it.
Mr. Rosenthal,
Mm-hmm.
is the y-intercept when y is 0?
Is the y-intercept when y is 0?
When x is 0. But you find the y-intercept by making y 0, right?
No.
No, you make
It's when x is
I want you to think
oh
that out.
x is 0.
Wait a minute. Think that out. If y is 0, what are you solving for?
Oh wait. Oh
You're
yeah, we're
solving
solving for
x.
y.
When y is 0, you're going to get not a y, you're going to get an x. When
Right.
y is 0, think of it as you're eliminating y when you make it 0. Well, then there's only x. So then you're finding out what the x-intercept is, not what the y.
Yeah, because if y is 0, then you need to find out what x is, because then if you multiply negative 2/3 by x and add it by 3, then that'll be y, which is 0.
Yeah, and then you could solve by getting x isolated. But now when you make x 0 and you eliminate this, 0 times negative 2/3 is 0. What are you solving for now? When you eliminate x, you're going to solve for the only variable that's left, y. Okay? So then y would be 3. And that's so 0x, if x is 0, y is 3, the coordinate is 0, 3. Where is that? Is it on the x-axis or is it on the y-axis?
It's on the y.
Yeah, so that's the y-intercept. All right, so the way I'm going to graph this, everybody's watching now, is I'm going to just identify the y-intercept in the equation without plugging a 0 in. I already know the number on the end because this is already in slope-intercept form from yesterday. So then I'm going to take the intercept of 3 and just put a point there straight from that. The second thing I'm going to do is I'm going to follow the slope. The slope shows a negative delta y of 2 for a positive delta x of 3. On the graph, I go down 2 and over 3. If I would like, I could do that again, down if I want another point, but 2 points minimum determine a line, so I could just make a line now. But maybe for more accuracy, if I'm going to use a ruler to try to connect the points, then maybe a third point might help my line be a little bit more accurate. So I'll go down 1, 2 again, and over 1, 2, 3, something like that. Doesn't matter. I'm doing Bob Ross today. Anybody know Bob Ross?
No.
Yes.
Woo!
So it would have been right there.
Yeah, he's great.
Doesn't matter. Right, and then he does his paintbrush against the side. He beats the devil out of it. Yeah, my geometry class, we were all doing Bob Ross sayings during the lesson. He's you can see him on Netflix. You know, he's got all those painting things. You know, and you can actually try
All
to
those happy little trees.
happy little trees. Exactly.
The B in Bob Ross stands for best.
Yes. Okay. Any questions about how to graph this using the equation? I did not make a t-table. Using the intercepts is good if you want to practice that. Doesn't matter.
So you went down 3. You went down 2 because the 2 is the y and it's negative.
It's the It's the delta y.
Delta y.
That's a y. That is a delta y.
The change in y.
And there's a difference, yeah. Changing something is not the same as the thing itself in a position in time, in space-time. Where something is at a given time is different than measuring where that is different than measuring how it's changed. So the slope is all about how it's changed or how it changes from location to location.
Okay.
Y by itself and the X by itself just represent X and Y locations.
Okay.
How do you solve the equation?
You don't. There's infinitely many solutions, remember?
Oh, yeah.
Remember, you can plug in as many kinds of X's as you want. That would make up the domain, all real numbers. You can try. You would never be able to plug in an X to violate any of our rules, right? Where you cannot have a 0 on a denominator. You cannot have a negative inside of a square root. These impossible situations.
Mr. Rosenthal, on the middle point, isn't 2/3 of 3 2, and then you move it up 3 more for the middle point?
2/3 of
Because-
3. Why are you doing 2/3 of 3?
Oh, is it negative 2/3?
Yeah.
Oh, okay. I didn't see that.
Mhm.
I thought it was the opposite.
But why were you saying 2/3 of 3?
Because the x is on 3 in the middle point, and 2/3 of 3 is 2. So then I thought it would move up 5 because I didn't see the negative, but now I see that it's a negative.
All right, but I don't think of it in terms of 2/3 of something. I'm saying that the 2/3 represents a delta y over a delta x. Okay. Any other questions?
For the middle point, how did you get 3, 1?
Because I came down 2 and I went over 3. I made a movement. I made a delta y of -2. And then you can't do that by itself. Delta y only happens when you get a delta x. So then I had a delta x that was equal to +3. Now, if you want to know where I got those numbers, you have not more than to look right here. The numerator is the delta y, down 2. It's a vector. It's like a direction. It's telling you go down that much, a magnitude and a direction. The direction is down because it's negative. If it was positive, the direction would go up, right? The delta x is positive, so that gives me direction to the right. Instead of if it was negative, it would go directionally to the left, and it gives you a magnitude. So think of the change as being represented as vectors, if you want. So I could put an arrow to show that it's moving. And it's doing them at the same time. So it's really not doing them in 2 pieces. It's really doing that movement.
Is it Mr. Rosenthal?
Yeah.
So all you have is just find the y-intercept and then graph it using slope.
That's one way to do it. The other way that we did it earlier was to make a t-table and get a few different solutions to the equation.
Okay.
So you need to know both ways and be familiar with both ways. You'll be tested on both ways. So you're going to need both ways in engineering. You're going to need both ways to understand algebra 2, pre-calculus, algebra 1, calculus, any of the math and the physics, all of it, you're going to need to know it both ways in terms of solutions to the equation and in terms of the components of the slope intercept. And there's other forms I told you guys about that we have yet to learn. So any questions about example 3? Lesson 9.5.
Yeah, I have a question. I still don't understand how you got to there because, like, I understand there's like -2/3, right? But then did you subtract 3 on both sides or what?
We started with the y-intercept.
Now there's more participants.
I started with the y-intercept.
There's one more.
I started with the y-intercept of 3. That's where my starting point was. Then the purple and the pink is the second thing I did. And then I put a point here where that ended up. Then I just went through it. So
Okay, that makes sense.
yeah, and then
But, like,
I mean, once you say that, and then you look, well, where did you get those things from? Then you just look at the equation and you see, oh, I see where you got the 3 from. I see where you got the down 2 over 3 from. Okay,
Yeah.
And this is only when it's in slope-intercept form, which is why we ended yesterday doing what? Turning all of those equations into slope-intercept form. Anybody else?
If you plugged in, say, the number 5 and
For
that
X?
was x, what would you do? Would you multiply that by 2/3?
-2/3, so you'd get -10/3 plus
Okay.
3. Let's examine what that does. What is -10/3 plus 3? Which is 9/3, right? 3 is 9/3.
Yeah.
So let me rewrite that as 9/3. You would get -1/3. So your coordinate would be, you plugged in 5, and the output was -1/3. That means that that point is on the graph, and you can check it. Here's 5, Negative 1/3 would be about a third of the way down to that point, right?
Huh?
There's 5 negative 1/3 right there. It's on the line.
Okay.
It's a solution. And other questions about this? All right, moving on. Good job. Try this one. Go.
What does that say? It says y equals x or
Negative x minus 2.
okay, thank you.
You got it. Try to make your graph neat. Space these tick marks evenly and straight. Otherwise, because some of you already have good penmanship and you don't have a problem with that. You don't even need to be told that. But some of you, every year for the last 16 years, not that you are the same people that came before you, but we're all very similar as human beings. There's a percentage of students that become our doctors in the future that have that messy handwriting. And I get graphs that look like this. I've seen it like this. See that? Can't even barely understand.
It's beautiful.
That's me.
But
Work of art, Mr. Rosenthal.
okay, there's a big gap between this and orange, and if it's not, my orange one is not that great. If it's any worse than my orange one, your graph's going to start to look sloppy. It will become unuseful because you will not be accurate in the point. You're not going to be accurate in what you're seeing. Graph paper helps because it already is spaced out for you. Okay, so it's good to have graph paper. But if not, and not everybody has that even right now, a lot of you don't, space this out as take a little bit of time to space it out. You don't need to get a ruler, okay? Just get used to being able to put one out there without a ruler that is kind of you're eyeballing and trying to space evenly, and you should be okay. All right, here we go. This is my starting point. By knowing what my slope is -1, and knowing what my y-intercept is, -2.
Mr. Rosenthal, how'd you get the slope like that?
It's right here.
Oh, yeah, because -x is also negative. Wait,
This is a marker, but it's also one marker, right?
why isn't it negative? You just remove the x from the equation.
This is not that equation.
Yes,
This is me identifying what the slope and y-intercept are.
-1 is.
Hold on. I did not get these by manipulating the equation.
you just extracted the
I did not get rid of anything from here. I'm just saying this is the slope from the equation. That is the y-intercept from that equation.
Okay.
All right, here we go. B is the y-intercept. That's my starting place at -2 right there. That's half the work. The second half of the work is the slope. I'm going to express it as a fraction so that I can see it as a delta y and a delta x. Okay, so I'm going to drop down 1 and go over 1. And I have my line. I can do that again, drop down 1 and go over 1. I can even go up 1 and to the left 1 if I want. Doesn't matter.
Oh, that was the.
I can go up 1 over 1 here because it's along the same line. Because if I go up +1 to the left 1 and you simplify that, that's -1. Or if I go down 1 over positive 1, a negative divided by a positive is still negative. They're the same. So going up and to the left is the same as going down and to the right. Okay, there's my line. Questions? Comments? Praises?
Concerns.
Concerns? All right, moving along. Example 4, here we go. A typical leopard gecko, didn't know there was such a thing, is 3 inches long at birth and grows at a rate of about 1/3 of an inch per week for the first few months. The total length of a leopard gecko, Y, that's going to be the total, that's what we usually have as the total, is Y, after X weeks can be represented by this equation. What's the 3? Why is that?
The starting length,
Why did it start at 3?
because it was born at that length.
Yeah, it wasn't born at 0. There would be nothing to be born. So it already had some length at birth. So this is not direct variation because it's born and we're starting the clock after it already has some length to it. Okay, then the 1/3 represents growth, growing, changing, right? And it's changing 1/3 of an inch per week. All right, so you have this equation. Go ahead and graph it and describe what the intercept and slope represent in the problem, which we kind of already just did. Did you guys catch the trick?
Yeah.
Not impressed, huh?
We're a tough crowd.
No, you're not.
You're very unfriendly.
We're tough as rocks.
We're the toughest crowd in the world.
The toughest crowd that gets pleased easily.
Look how I made my coordinate plane. I accentuated quadrant 1. Notice how I've had barely any quadrant 3 or 4, and I have a little bit of quadrant 2. I don't need it. And there's a reason for that. Because I'm able to look at this and say, oh, my starting point is in quadrant 1, or it's up above. So that gave me to accentuate up instead of to accentuate the negative part of the graph, right? And then my slope is going to move up from there. So I know already without doing it that I'm starting up and I'm going to go up from there. It's going to look like this somehow. Now, how flat or steep it is going to be determined by me actually doing the change. All right.
Is it Mr.
Let's go Neapolitan. Here we go. Starting point. So have a slope is 1/3. Y-intercept is 3. My y-intercept is 3. That means that's going to help me understand what these things mean. We already talked about it. And then from there, my delta y is 1 for every x of 3. There it is. What does that y-intercept mean?
It's the starting length. It's the length at birth.
Yeah. Why does this not make sense back here? What is x measuring?
Growth.
What's happening
Is
along
it time?
Time.
time? So starting here is at 0 time. Now you're going back in time I guess you can go while it was growing from a zygote. If geckos have a zygote phase, I don't know the biology, but I'm sure it didn't go from 0 to 3 inches. It had to get there. So I guess
Yeah.
this would be before it was born. You could do that, but then at some point it would stop, right? Because at some point it hadn't been, that process hadn't been. There was no conception of it. Okay. So, but anyway, then we move on with this line. So the math can keep going, but the practical situation could be different. And the graph might not always make sense for a practical situation. Remember, math is used as a tool to help us with our practical situations. Okay.
Yes.
All right. What does this slope then mean?
It's the constant rate of change or constant rate of growth.
It's the rate of growth of the leopard gecko.
Yes. Which
Wait,
is
then
one
wouldn't
third-
the graph on the right side also change at some point since it doesn't grow
Yes.
at 1/3?
Exactly. So this arrow would not go on forever because it's not going to keep growing.
It would
It's only going to
stop
grow for a few months, right? So this graph is only going to represent
a line. It would be a line.
this graph will only give you a predictability for a certain amount of time, and then it will stop. And then what will actually happen to the graph eventually?
It would.
Will time stop?
No, time will keep going.
Okay, but what will not happen is it will not grow anymore.
Yes.
So the line will flatten out.
Yeah.
Okay.
So then, so the line would go from a 1/3 change it like 1/3 slope to a 0 slope.
Exactly.
Mr. Rosenthal?
Uh-huh.
And then the flat line would stop once the gecko dies or something?
I guess so, yeah. Death of the
Or would
gecko.
It would go down because the gecko's
No.
getting eaten.
But assume that
would
the
be
gecko didn't lose any length to it when it died.
Yeah.
It died at
It
that
would
length,
be
and
the
that's
same
where
thing.
it
It would
ends.
be the same.
How can it go to a negative length?
What about when it was born? It must have started at 0, right? Or close to 0. So this would go down till until the x-intercept, right? Say it like
Yes.
that. It would start from a 0. Before that, there was time, but not for this gecko. So the
This
life,
one was non-existent.
this is just representing the gecko's life. Before birth, at birth, growth, right?
And then death.
Now, we don't even know if the growth of it was the same before it was born, right? So the growth could have been steeper before it was born and then changed to a flatter one after, or maybe it was even
It
slower.
can't go to a negative length though.
This is not length back here. This is time.
It's time.
Right. You can't go negative length, so that means you cannot dip below this. Remember,
Yeah.
up above and below is length. So this
Mhm.
line can't you'll never see this line go down here. You won't see any points down here. Right?
Mr. Rosenthal, this kind of relates to, I mean, like like distance equals time times speed, or like
Rate times time, D equals
rate
RT.
times time. Because like the slope would be the rate, and then basically the distance, which would be like represented by y, it would be the length, and then time would still be x, and then the rate would still be the same.
It would be the change, yeah.
Yes.
Exactly.
Here's what I don't understand. What's it called? I understand how you had 1/3, but I don't understand why it's just like increasing 1/3.
It's going up 1/3. So
It's growing.
1/3 of an inch per week is one way to think of it. 1/3 of an inch per week. Or you could break it up into 1 inch every 3 weeks is how we moved it, right? If every one of these notches down here that we had was a week, 1 week, 2 week, 3 week, and each one of these was 1 inch, we can say that it went up 1 inch in 3 weeks. It went up 1 inch, and it took 3 weeks to do that.
Also, wouldn't it reach a max?
Yeah, it would reach a maximum and then it would flatten. That's what we flattened it. We don't know when it's going to flatten, But when it reaches its maximum length, then the line doesn't end because time goes by, it's still alive, it just stops growing. There's no more growth.
Growing 1/3 inch per week is pretty like a significant amount per week.
Yeah, now if I wanted to show that, what's confusing is what if I break that 1 inch into thirds, here and here.
And then you would have to go over 1 week.
If I go up a third, then I go over 1. That's still on the line. If I go up another third, right? If I go up another third, then I go over 1, then I'm
still
here.
on the line.
And then if I go up a third, then I've gone up 1 whole and I've gone over 3 times. Okay, that's why you can think of it either way, 1/3 of an inch in 1 week, or you're allowed to break that up into 1 inch every 3 weeks.
To be whole numbers.
Yeah, to be whole numbers, right. Does that help you, Kieran?
Yeah.
Okay, good.
Close to like 1 inch a month.
Mr. Rosenthal,
Yes.
how would you find out the length that it grows in a day? Would you just multiply it by 7?
Well, that we can come away from the problem and just look at this goes back to that chapter on conversion of units. So if you have 1/3 inch per week, dimensional analysis, you want to know what it is in a day? So how many days are in a week?
7.
Days.
Okay, I'm going to make a fraction. I want to get rid of weeks. So where's weeks going to go?
On top.
On top.
Days are going to go here. Fill it in. 7 days, 1 week, weeks cancel out. So now you have 1/3 over 7.
It's 1/3 per week.
Which is the same as 1/3 multiplied by the reciprocal of 7.
1/7.
1 over 21. So that means you can think of it as 1 over 21 inches per day,
Yeah.
because now we're in days. Or you could think of it as 1 inch every 21 days, if you want whole numbers.
Got it. Okay, thank you.
Well, you can guess that from the 1/3 a week, because after 3 weeks, then it's 1 inch.
Okay. Anybody else? Questions? Expansion on this?
Rosenthal?
Yeah.
So does the top of the fraction represent the x?
Nope. Delta y.
So the top represents delta y, and the bottom represents delta x?
Correct.
Okay.
Right. All right, moving along. Hey!
Homework.
All right, I'm going to write
Work, yay.
down.
That's all.
This is due tomorrow.
Internal
Or today?
No, it's not due tomorrow. We'll make it due next Friday.
What? Next Friday.
Next Friday.
You got a problem with that?
Why not? tomorrow?
No, we
Why
don't.
not
No, we don't. We don't have a problem with that. Totally no.
That's great.
I am doing this because of the circumstances are difficult for some people and not for others. Feel free to do it tonight. I recommend you do. Don't look at the deadline.
Free time.
Don't look at the deadline being next Friday. Don't look at that as what I'm suggesting that you do. I suggest that you have this done by tomorrow.
Yeah.
Look at it as some people have some difficult situations, and it's for those people. It's for those people. It's not for you. It's not for everybody to take till next Friday to do. Everybody got it? If not, find it on YouTube. Okay, going on to 9-6. 2 lessons to go.
And then we're on lesson 10.
Chapter 10.
Oh.
Lesson 10.
uh,
Lesson 10.
So remember, when we start a section, we get all the good problems. We get all the meaty challenge problems. So that being said,
What's this chapter about?
don't get discouraged. We're still in the same chapter. You mean the lesson? You'll see. Wait till we do the warm up, and then we'll tell you what it's about. Okay, so don't get discouraged if you're having trouble with these. All right, just ask questions. All right. So describe a line that has a y-intercept, but no x-intercept. And then give me the slope of that line and put that information in the chat. Don't shout it out. Go.
A y-intercept but no x-intercept?
Mhm.
Oh.
Ah.
I probably spelt it wrong.
Mr. Rosenthal?
A parabola is not a line.
Mr. Rosenthal?
Mhm.
I think
I typed something in the chat. I just wanted to see if it was like, if I.
Everyone, come on!
Mr. Rosenthal, am I
Somebody was
correct?
telling me something and then you didn't finish your thought.
I typed something in the chat. I just wanted to see if it was a correct statement.
Same with me.
Who's that?
Shy.
Who's shy?
Oof.
You said right. Oh, like the gecko problem?
Yeah.
You mean for this warm up?
Yeah.
No.
And Mr. Rosenthal, am I correct? Because
It is vertical.
I don't know. You're gonna see. We're gonna go over it.
oh, come on.
Bruh.
It got buried in the chats. I don't want to scroll up.
Oh,
I'm looking now. Vertical is not correct.
not vertical.
If you put a vertical line,
That would be undefined slope.
well, it didn't say that it couldn't
Am I
be.
correct?
But if you do a vertical line in red, you're gonna have an x-intercept right there because this is the x-axis. You're gonna cross it. No x-intercept. This wrong, bad, no, because you have an x-intercept. This said no x-intercept. This can't be. A vertical line does go through the x-axis. What you need, my friends, is a horizontal line.
Array.
Yes.
Oh, okay.
As long as y is not on, as long as the horizontal line is not on the x-axis, anywhere else, even if it's close,
I
any
did it.
horizontal line other than the x-axis, and the slope would be what, everybody?
0.
0.
Yeah. And all of these have y-intercepts, different y-intercepts. As long as the y-intercept is not 0, then you're not going to touch the x-axis. Okay?
Yeah.
All right. See if we have anything else. Sometimes we have a whole bunch, sometimes we only have one. Here we go, we got another one. Suppose the graph of a line has a negative slope. So the growth is negative. That means something's decreasing, something's shrinking, something is getting less over time, right?
Shrinking from left to right.
You're from left to right, exactly. So as time moves forward, we do left to right. Suppose the graph of a line has a negative slope and a positive y-intercept. Through which quadrants does the line pass? Put that in the chat. You don't have to justify in the chat. We can justify it as we talk about it. Go ahead.
Okay, could you the quadrants? Is it
In this situation,
clockwise?
quadrant.
You guys can openly talk about it.
1, 2, and 4, in my opinion.
How does it go through 2? Oh, yeah, it does go through 2. Because if it
it's counterclockwise.
how can a line be counterclockwise?
No, I'm talking about
How the quadrants.
I'm talking about the quadrants, like
Oh, yeah.
yeah.
Because
I'm
it's
talking
like
about a line.
Is that a positive y-intercept?
and
Yes.
Yeah.
negative.
That's a positive y-intercept.
Negative would be below the x-axis.
I just have to get the quadrant numbers right.
Negatively sloping.
Yeah, I put that.
So some of the line is in quadrant 2.
Yes.
Some of it's in quadrant 1. Some of it's in quadrant 4. In some practical situations, you can't go back in time, so you won't be able to cross this point. And in the problem like with the gecko, you can't have negative length. So sometimes we just get this quadrant 1 in our practicality, and the boundaries are the intercepts.
That makes sense.
Yeah, because you can't go negative growth unless unless you're like
negative length be?
Negative length, it would be, I mean, like you would be like decreasing in length, because like that's
Decreasing from what length?
your original length.
No, that's just a y-intercept negative.
No, if you were decreasing from your like starting length, then that would be the y-intercept going. That would be this problem.
Can anybody think of a situation where something decreases as time goes by?
Oh, if you spend money.
How about gasoline?
The mass of ice.
No, but that doesn't.
Gasoline in your car.
Food. Yeah. Oh yeah.
Oh, I was just gonna do the mass of ice.
How about we drive a car with a full tank? With a full tank, you can't go more than a full tank, right? And you can't get less than 0, right? And then you just drive until you run out of gas. Well, that's going to take time, so you're going to move that way, and then your gas is just going to keep going down. And if you just put your car on cruise control, you're probably going to burn gas at about the same rate if you go on a flat road.
Hopefully, no one drives until they run out of gas. They actually go to a gas.
Well, I'm just giving you an example of what that would be. And then you run out of gas, and then you can't go. It doesn't go past that, and you can't go before the full tank. You're measuring it once you start with the full tank. All right.
And you have to walk to
Moving along.
Would the negative of it be filling it up?
That would be the positive.
You mean this?
The part in quadrant 1, would that be filling the tank up?
The X-Files Luminati.
This is a full tank of gas.
Yeah.
This is gas in the car, amount. The axis is amount of gas. So these points as I'm moving back to the left are showing more gas because they're higher. This one's up here, this one's up here, right? They correspond with some value on the y-axis. And you're moving up, 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 up. Okay, I'm moving now. Thinking about it this way, this is time, intervals of time going forward.
Yes. So if you had to fill it up, you wouldn't be going the opposite direction. You would still be going forward because you're going forward in time and you're taking time to fill the tank back up.
Now I can have a separate graph. Now I'm at the gas station. All right. I'm at 0. I'm maybe just slightly above. I have a tiny bit of gas. So I'm right above 0. Is where I'm starting.
Cutting it close.
Okay, now I put the money in and I put I plug it in and I pull the handle and the gas starts filling up, and that's taking time, right? Time is still ticking away. Now the gasoline in my car is increasing until my gas is full. See that? That's it. And then that's it. I'm done. All right, so that's the end of it. That's what that would look like. Okay.
Why, if the line went the other way through through quadrant 1, 2, and 3, would it have a positive slope, or why can't it do that? Because it doesn't cross through a negative y-intercept, so why can't it just be the other way?
Okay, well, if I have this, that's 1, 2,
negative time.
3.
That's going back in time.
If it goes through 1, 2, and 3, it's impossible to have a negative slope. How can you draw it going down from left to right, but still go through 1, 2, and 3? Let's draw all the ways I can do this. What if I went through 1, 3, and 4? Okay, it has to be a negative slope. If I go through 3, 4, and 1, it has to be a positive slope. Of course, I can always go through the origin. Then I can have anything I want because I'm going through the origin. That's only one point. There are infinitely many lines you can put through a point. So I can have up and down, I can have side to side, right? But I can't have side to side here and still go through quadrant 3. A horizontal line going through will never go through 3 or 4. a vertical line, let's say, going through 1 and 4. Well, that will never go through 2 and 3. So if I'm trying to hit 3 different quadrants, you're going to have, unless I'm going through the origin, which you can do any line through the origin because it's a single point. But if it's anything other than that, and I'm trying to go through 3, either it's got to be positively sloping or negatively sloping. And then you can see the cases where it's negatively sloping and the cases where it's positively sloping. All right, let's move on.
If you did a parabola, you could go through all 4.
Well, that's when we get to parabolas.
Yeah.
All right, describe what happens to the graph of y equals 3x plus 4 when the slope is changed to 1/3 instead. Put it in the chat. This one, you don't have to draw anything. You just answer.
I can't. Wait, so is it y equals?
You start with y equals 3x plus 4, and the only thing you change is the slope. Change it to 1/3. Now, if you want to if you're not sure what happens, graph the 2 different situations and see what happens. And then, but if you already know what's going to happen, just describe it in the chat. It's something you can simply describe in words.
So, Mr. Rosenthal, it's like the comparison of the line of y equals 3x plus 4 in comparison to when the slope is 1/3.
Say that again.
It's like so we're describing the difference between, or like.
You're describing what happens to the graph.
Oh, okay.
The slope was 3. Slope was up 3 over 1.
What changes in the graph?
The slope changed to 1/3.
Then it was up 1 over 3.
What did the slope used to be? 3 over 1?
Yep, and so that's what I showed here. Now,
Gotcha.
Now you're going up 1 over 3.
There you go. It's different.
So describe the difference in the pictures. The pink line to the blue line. What happened to the blue line when it became the pink line? How would you describe it? Somebody said, John said, less steep. That's right. There's another way we say that.
It flattens.
Flatten. Yeah, it flattens it. What if I keep making the fraction smaller? What if I make it 1/5?
Then it becomes
closer to a horizontal line.
It becomes
Okay,
closer to
so
the
up
axis.
1 over 5 is way over here. So it's going to be like that. And then 1/1,000,000th.
Oh.
Right? It will look like 1/1,000,000th is going to look like a flat line, but it's not exactly.
It's not.
Because it still went up 1, but it went over so far that it looks like a flat line. Okay?
The only flat line is once the slope is 0.
Keep making that fraction bigger. Make the denominator, call it a variable n, and let's let n go to infinity.
Oh.
Then what happens?
It's like if you increase the denominator, then it's gonna keep flattening out.
What happens if n goes to infinity?
Well, it
What
won't
happens to the
be.
line?
It won't be exactly a flat line.
Oh no.
No, it won't be exactly.
because
It won't be exactly flat.
Because
It would be flat. It would be 0. It would go to 0. When the denominator becomes infinity, this goes to 0.
Oh.
Why?
It's just something that happens with infinity.
There's no reason for it.
Oh yeah, because it's like close to 0.
All we can see is what the approach is. What we have no reason to believe that the pattern of approach changes. And what we see is that the number becomes ever closer to 0. Right?
Mm-hmm. Yeah.
So by saying infinity, you're basically saying, okay, complete the pattern. Well, then what you do is you look at where is the pattern going? What is it approaching?
0.
Well, it's approaching 0. So if you could go all the way, which you can't, and that's why you're having trouble understanding that, well, it's going to go up 1. Well, But you're seeing what is the pattern if you could keep going. The pattern is it's approaching some number. You ask yourself, what is that number? And then when you say what it is, you know that that's, if you were able to reach infinity, which you're not, then it would be 0. So by me saying, okay, make that infinity. Well, you couldn't, you're saying, well, when you make that infinity, it doesn't, you can't get to 0. Well, you can't make something infinity either.
Yeah, exactly.
All right, so you're already starting with so I'm saying conceptually we can. Conceptually, we can say, all right, if we can violate that and go to infinity, then you can go to 0, because that's the pattern is showing that you're going to 0. And that is the principle of pre-calculus and calculus of a limit.
Okay.
The way that looks is this. The limit as x approaches infinity of this function, which is not, it's 1 over x. Okay? And that is equal to 0. That's a pre-calculus problem right there. All right, anyway.
Smart enough to be doing pre-calculus now?
Yeah, you're doing pre-calculus now. You basically don't even need it now. You get to just move straight on to calculus. Just kidding. All right, oops. All right, that was flattened out. Hey, my trick didn't work. We're gonna edit that out. Just kidding. Okay, try this one. I'm gonna read this one to you. Graph y equals 3 times the absolute value of x plus 5. Your graph should look like an angle. Give the slope of each ray of the angle and the coordinates of the vertex. Try to work your way through that problem. Go.
Is that plus or times 5?
That's 3 times the absolute value of x plus 5.
Okay, thank you.
Oh.
This one you might use a t-table would be a good use. A good tool.
So, Mr. Rosenthal, would you recommend always putting the y-intercept in the t-table, or?
You can, yeah. Putting your intercepts in the t-table is a good idea.
Mm-hmm.
Mr. Rosenthal, is it just a matter of plugging things into this equation?
Mm-hmm.
Okay, that seems pretty simple.
Can be, yes.
Oh.
Look how I'm cheating on my graph. I'm putting barely anything down here.
Cheater. How dare you, Mr. Rosenthal?
Oh, yeah, I see it now. It's because it's the same, when it's the inverse. It was the additive inverse of a number would be the same value for y. Because -1 would be, if x was -1, and it would be the same value if x was 1, because it's the absolute value.
Look at my coordinates that I'm going to try. I want to see what happens on the left and the right of 0.
Well, yeah. I know it's going to happen.
Don't you get a v?
Yep. You're going to get it. They're saying it's an angle, but that's fine. But, all right, everybody.
Mr. Rosenthal?
Angle?
Yes.
Well, it would be.
Wait, is the x coordinate 3 times the absolute value of x, and that's the x?
Well, here are different x's you can plug in. There's still an infinite amount of solutions.
That's the v, yeah.
Now, your domain this time is still the same. You can put anything you want for x. There's nothing that's going to violate anything. You're allowed to have both positives and negatives in here.
It's just going to turn into the magnitude.
No matter what, this is going to be positive. A positive times a positive is a positive. Plus a positive is, so y can only be positive. Not only that, no matter what you put here, The lowest that this could be is going to be 0. At the lowest, this is 0.
Which is the y-intercept.
Plus the 5. So as a matter of fact, this graph is not going to be able to drop below 5. 5 is going to be the baseline on this. All right, so let's try it. When x is 0, then the absolute value of 0 is 0. 0 times 3 is 0. 0 plus 5 is 5. 0, 5. My graph will not go below this imaginary line. It will not drop below that. It cannot drop below that. There's nothing you can put in here that's going to take away value from the 5. No matter what negatives you put in there, they will be turned into positives. Let's try a positive one. X is 1. Absolute value of 1 is 1. 1 times 3 is 3. 3 plus 5 is 8.
Okay.
Okay, so 1, 8. Okay, put in a 2. The absolute value of 2 is 2. 2 times 3 is 6. 6 plus 5 is 11. Notice what's happening here. What are these increasing by?
3.
3 for every delta x of what?
1.
Delta x is 1. Delta y then is 3. Okay, that's because of the slope is 3 still.
3, 1.
Just because of the absolute value, we still know now from doing this, we realize that that still is the slope. That didn't change the fact that that's the slope, and it didn't change the fact that that's the y-intercept. So that's nice to know. What's nice to know is that when we do absolute value, that the slope didn't change and that the y-intercept component of it did not change. What is going to change is that instead of the line continuing, so where's 211? It's up here.
Thank you.
So instead of the line doing this, that's what normally would have happened. The line would have done that because negatives would have kept dropping down, right? But let's now investigate what actually happens. Put in a -1 now. What is the absolute value of -1?
1.
1. Now all of a sudden the absolute value did something. When you put a negative in is when it changed. Okay, so now 1 times 3 is 3. 3 plus 5 is 8. You're going to get the same answer as +1. -2 will give you the same answer as +2. It's like a reflection in a mirror. Right? If the y-axis is a mirror, then the right side of it is going to look just like the left side of it. It's going to be a mirror reflection of it. Okay? So then -1, 8 is here. -2, 11 is here. You're going to get this V. Okay?
A vector.
All right? I'm going to make that solid because that's what the actual graph is. The dotted stuff is not the graph. This dotted would have been the graph if there was no absolute value there. Okay? What's the slope of this one? Of this ray? This is a ray because it has an endpoint and it goes in one direction. What's the slope of this?
+3.
The delta was, it's 3. Goes up 3, 1, 2, 3, over 1. Up 1, 2, 3, over 1. So 3. So slope is 3. What's the slope of this one?
-3.
Negative.
This one goes down 3 over 1. Down 3 over 1. So this one is
-3.
-3. Okay?
Yep.
All right. All right, so it looks like we're going to be getting into standard form and trying to make the equation go from standard form to slope-intercept form. This is going to get tricky, so I want to save tomorrow to be working on this.
I thought we already did that.
I showed you an example of it, but now the lesson's going to have a lot of examples doing that.
Oh.
Okay, and we're going to have some problems where it's more practical to use standard form. All right, so we're going to investigate standard form tomorrow. So you are now a little bit early, dismissed, and I am now on office hours.
Bye, Mr. Rosenthal. Bye. Thank you.
Bye.
Why are we 4 minutes early?
Bye.
Because we were saving the
Planet.
Bye, Mr.
And
Rosenthal.
it's one of the benefits of not being in a structured school site. You can't be released early from class. Now we have so much more efficiency because when I'm at a good stopping point, then that's when we stop. Not
Bye, Mr. Rosenthal.
all right. Bye. Not necessarily when the bell rings.
right now we would probably be doing Simon Says or the clap thing.
That's right.
Mr. Rosenthal, so
Yeah.
I have a question about the homework.
Okay.
So one of the questions, number 6, it says, determine if the relationship between the two quantities is a direct variation. And there's a graph that does have a constant of variation, but the line doesn't go through the origin.
And it's not an example of direct variation.
Okay. So also number 8, the equation y equals 350x plus 5 represents the number of dollars y Kristen charges for driving you X miles in her taxi. Determine if there is a constant variation. If so, explain what it represents.
I'm guessing it's $3.50. When you said 350, you didn't mean $350, right?
No, I meant $3.50.
Yeah, okay, so the cab is going to be charging you $3.50 per whatever, per minute or whatever that is, per mile. It probably says it in the problem.
Yeah,
what is
it says for X miles.
Okay, so it's $3.50 a mile, right? But that means,
yes.
What if people want to use the cabs to just go across the street? Then you're wasting the cab driver's time because you're not going a mile. They can't charge you. So what they do is they put in that if you're going to use my services, you have to pay a minimum of $5 if you don't even go a mile, right? So that explains that starting amount. But that makes it not direct variation. Now, what is your question?
Would there still be a constant of variation?
Yes, 350.
Oh, there's a, okay.
They're not going to change, the cab driver's not going to change the fee per mile in the middle of driving.
Yeah, so it's going to be, oh, okay, I get it.
It's the slope. There's still a slope.
Yeah, it's just not direct variation because you didn't start at $0.
There's a y-intercept.
Yep.
There's a b.
Once I heard somewhere that
thank you.
All right.
seahorses have to constantly eat, but I'm not sure if that's true. But just like,
Who has to constantly eat?
Seahorses.
What kind of horses?
Seahorses.
Like,
oh, seahorses. Oh, okay.
Because they have no stomach, I guess. But I don't know.
What?
That sounds like a Snapple fact.
Yeah, it was like
Seahorses don't have a stomach.
game that I was playing. But yeah, it was kind of weird.
Okay.
Goodbye.
Bye.
So, Mr. Rosenthal, a question, like, what chapter do you think I should start in the green algebra book? Like, because I did the chapter. I was reviewing the factoring because we just got back from a break. But I remember one time I did like chapter 12 in that book.
Yeah, now that you're going to get the book, you didn't already get it yet, did you?
No, it's coming.
Once you get it, start in chapter 6, take the test again. Check all your answers afterwards.
Right.
And then just go 7, 8, 9, 10, 11, 12.
Okay.
Okay?
Is it coming tomorrow? Oh, it's coming tomorrow, yay.
And do every page. Do all the extras.
Where do you get the challenging problem?
The challenge problems, especially the challenge problems, but you're going to see that some of them are ones that we've done. And then they have extra pages that are not part of the lesson for, you know, like airplane problems or, you know, I don't know, just
Oh.
extension, application stuff. Do all that. Do everything that the book has to offer. All of that stuff is all good stuff that they have in there.
Okay, cool.
And take your time.
Yeah.
Where do you get the green algebra book from?
Maybe Jasper can send you a link.
Do I have this person's phone number?
Who is that?
Oh, it's Jonathan.
Oh, Jonathan.
I don't think I have your phone number, but I think, wait, Jonathan, do you have Ben's phone number?
Yeah, I do.
Okay, so then I can ask him to send it to me if I will. I'll send you the link.
Perfect.
Okay.
All right. Thank you,
Anything else?
Mr. Rosenthal.
You're welcome.
Bye.